Well, I won't do all of the examples in assignment 7, but let's do a few of them. Starting with number 1, prove or disprove the statements all bears can fly. Well, we'll find a counterexample. I mean, that's false. And to show it's false, what I need to do is to find a counterexample. And an obvious one is the ostrich. That's a bird that can't fly. So we've got a counterexample. Okay? Well, now let's look at number 2. Prove or disprove the claim for all x in R, for all x and y in R, x minus y squared is greater than 0. That's also false. And again, to prove something that's a universal quantifier, just like the one above it, it's a universal quantifier, or in this case 2 universal quantifiers. And to prove that a universally quantified statement is false, what you need to do is find a counterexample. Well, that's one way of doing it, at least. And the most obvious one here, well, anything that takes x and y equal will do it. So let's give a specific counterexample. Let's take x equals y equals 1. And in that case, x minus y squared equals 0, and 0 is not strictly greater than 0. Okay, came close, right? If we'd excluded x and y being 0, then we'd have a positive result. But it says it's true for all x, y, and r, and a single counterexample is all it takes. And in this case, any pair of equal numbers gives us a counterexample. Okay, number 3. Prove that between any two unequal rationals there's a third rational. So let's let x and y be rationals, x less than y. Okay, then because they're rationals, x is p over q. We can write y is r over s, where p, q, r and s are integers. And we have to show there's a number between. Well, the obvious thing is to take the mean. Let's just take x plus y over 2. And if that's rational, then we'll have proved the result. Well, here's the proof that it's rational. X plus y over 2 is equal to p over q plus r over s over 2. Okay? Which is p s plus q r over qs all over 2, which is ps plus qr over 2, what was it, qs? Can't see underneath my hand here, which is rational because it's a quotient of 2 integers. But of course, x is less than x plus y over 2 is less than y. And we're done. Okay, that's 1, 2 and 3 knocked off very, very quickly. Let's go on to do, I'll do number 7, the one about square root of 3. Well, just as we did with the square root of 2, we're going to prove it by contradiction. So I'm going to assume square root of 3 were rational. Okay. Then I could write root 3 is p over q, where p and q are natural numbers. And I can always assume that they have no common factors. Okay, because if you pick a pair of integers, a pair of natural numbers that do have a common factor, you can cancel it out. So you can always express a rational number in that form. Then if we square that, I get 3 is p squared over q squared. So I can multiply across by the q squared and get 3q squared equals p squared. So 3 divides p squared. But 3 is prime. And if a prime divides p squared, that means 3 divides p. If prime divides a pair of numbers multiplied together, it divides one of the numbers. So 3 divides p. So that means p is of the form 3, let's call it 3r. Okay, so that means p squared equals 9r squared. So I can take p squared and substituting it back in here to get 3q squared equals p squared equals 9r squared. So if I'll forget the middle term now, 3q squared equals 9r squared. Let me factor the 3 out. I've got q squared equals 3r squared. So that means 3 divides q squared. But if 3 divides q squared, then just as before with p, that means that 3 divides q. And now I've got a contradiction. Since p and q have no common factors. And yet we've just shown that 3 is a common factor. So there's a contradiction. Almost exactly the same as the one for square root of 2. So if we compare the two, CF, the proof for square root of 2, in the case of the square root of 2, we talked about numbers being even. But if we talk about something like p being even, that's just another way of saying 2 divides p. So really all I've done here is I've taken the previous proof, the one for root 2, and instead of talking about it in terms of even and odd, I could recast it in terms of whether it's divisible by 2 or not. And then the fact about 2 that we used there, we said if 2 divides p squared, then it divides p, it used the fact that 2 was prime. So I might just as well use 3. So it's exactly the same proof as before, except instead of talking about divisible by 2, I'm talking about being divisible by 3. I didn't express it that way before. I talked in terms of even and odd, but even just means it's a multiple of 2. Okay, well, we've moved on. Let me decide which one to do next. I think I'll do number 8. That shouldn't take too long. So we'll do number 8 next. Okay, so the converse of an implication, of a conditional, is the implication in the opposite direction, where you swap around the antecedent and the consequent, but everything remains more or less otherwise unchanged. So the converse of this is if the yan rises, the dollar falls. We just swap them around. Same here. If negative y less than negative x, then x is less than y. And in the case of C, if two triangles have the same area, then they are congruent. Now, in terms of what we're doing, this is totally trivial. This is just swapping things around without doing anything. What I'm really trying to get at with this exercise is in part to sort of contrast it with the contrapositive, and also to observe that truth and falsity can change. In this case, we start out with something that's true. This is a true implication. That's a true implication too. So sometimes the converse of a true implication is a true implication. Let's look at this one. If two triangles are congruent, they have the same area. That's true. But this one, if two triangles have the same area, they're congruent, that one's false. So sometimes the converse of a true statement is true, and sometimes the converse of a true statement is false. Now that's a different situation from what we find with the contrapositive. But when you swap round the order, you can sometimes get truth go into false, and you can sometimes preserve truth. Okay, well that's really all there is to that. It was just to sort of give an opportunity to reflect on these things and to recognise that truth and falsity plays its own game when you're dealing with converses. Okay, let's go and do number 11. Okay, that was that one about the irrational numbers. Well, we've already looked at some of these in the lecture where we've observed that some of them are rational. Let me see, we observed that this one can be rational. We observed that this one can be rational. And there's an issue about this one being rational. Okay, these were easy, we did those in the lecture. That was a later issue. That leaves 1, 2 and 5. They're the ones where they're irrational. And so we have to prove them this time, okay? And so starting with number 1, say, what we're trying to show is that it is irrational. So yes, it's irrational, okay? And let's see. Suppose suppose that r plus 3 were rational. Okay? That's a plus sign there. Then r plus 3 would be of the form p over q, where p and q are integers. Where then r would equal p over q minus 3, which is p minus 3q over q, which is rational. And that's a contradiction. Because r is assumed to be irrational. And we've shown that if r plus 3 were rational, then r would have to be rational. And the others are similar. You simply assume the contrary, you express it in terms of p over q, and then you do a tiny little amount of manipulation, and you end up showing that the number r is rational here, and that square root of r is, and that r is rational in the square root example. Okay, very straightforward. Nothing really more to be said about this one. Okay, the only one left now to do on assignment 7 is question 12. So let me just quickly go through question 12. Well, the key facts that you use in dealing with all of these are that if n is even, then, and actually it's an if and only if, then n is 2k for some k, some integer k. Okay, and that n is odd if and only if n equals 2k plus 1 for some k. Okay, the even numbers are the ones that are multiples of 2, and the odd ones are the ones that are 1 more than a multiple of 2. Okay, they're in between the multiples of 2. So, for example, if we do part A, if m and n are even, then we would have m equals 2k, for example. We'd have n equals 2l. So m plus n would equal 2k plus 2l, which is 2 into k plus l, which means it's even. It's 2 times something else. Do I need to do one more? Well, let me just do one more anyway, just because I'm on a roll now. Let me do number D, part D. If one of them's even, it's 2k, and the other one's odd, it's 2l plus 1, then m plus n equals 2k plus 2l plus 1, which equals 2 into k plus l plus 1. Okay? So it's twice something plus 1, etc. for all the others. Okay. Nothing terribly deep about these things, but in terms of writing out a proof, it's basically a case of just characterizing evens and odds in this way and doing a tiny amount of algebra. Okay, that was a very easy assignment, I think. Well, it was meant to be an easy assignment. It's easy for me to say that, right? I've been doing this for years. If you haven't met this kind of thing before, then it probably isn't an easy assignment. I fell into the trap of mathematicians there of saying something's easy in the same way we talk about trivial. That's a sort of a term of art that we use in the game. So everything's easy when you know how to do it, right? Okay, but I was looking ahead to assignment 8, which was decidedly difficult for me and for you guys. Okay, assignment 8 coming next is difficult.